So far in linear regression, let's say we have like some set of features. So only gonna have like one feature. Let's say we have like let's pick a really good example. So let's say for our car data set, let's say we have like a horsepower, the horsepower of the car. On our x-axis. So on our x-axis we have the horsepower, and on our y-axis we have like the price of the car. So based on the horsepower of like each individual cars, we want to predict the price. So let's say we could have like, okay, this is just like a little example. It's not like exactly how it is in real life. So let's say we have 20 horsepower, 40 horsepower, 80 horsepower, 100 horsepower, and we want to predict the price. So let's say the price for this car could be like, let's say $100. But $100, we got like $200, and we got like $300. So let's say we have like, let's say we have a car that has like 40 horsepower, and we have another car that has like 80 over there. Let's say we have like different cars, and these are their horsepowers. Let's say we just plot it on the graph. And now we want to, so basically we give this our model. So once our model learns from this data set that we give into it, so like for this car with like 40 horsepower, the price is like roughly around $100 or something. For this car over here with like I wrote 80 over here, 80 horsepower, the price over here is like, let's say $130, $35, not to scale. So now what we want to do is that we want to fit a line, and not just any line. We want to fit a good line whereby, okay, let's say something like this. There could be a better line, that the distance between this point over here and the line, so I'll use a different color. So the green will be like the distance from this data point over here to this line, this data point over here to this line, this data point to this line over here, which is the sum of square, the errors. I mean, we could use like different, how should I say this, measurement factors. So let's say it could be like the mean square error, could be like the root mean square error, different ones. And we want to make sure that the line that we drew over here, the error will be very small. So over here, let's say like, so if you're familiar, of course, the equation y, which is going to be our price, m, which is our coefficient, x over here is our horsepower. So I'll just draw something like an arrow down over here. The x over here is our horsepower, plus b, which is our intercept. So what our goal now is to find like these two values over here, to find the best coefficients that when we use this, when we plot like, you know, these data points, so this like the horsepower times this coefficient plus this one, when we draw the line, the error that we're going to get is like very small. So a really good algorithm that is really good for finding these two values for us is it's now we call it gradient descent. Yeah. So over iterations, let's say we could start like with an assumption. Let's say our assumption over here could be like this line over here with the coefficients from this. So let's say this is like this could be like a number. It could be like 2.1, and this could be like 5. And once we like, you know, put these together, so let's say 40 times 2.5 plus 5. But Okay, this is not like the exact one, so just get the idea. So let's say we start out with this assumption over here, then we calculate the sum of squared errors. So this is from this point over here to this line over here, from this point to this line, from this point over here to this line, and the mean square error. Okay, if you're not familiar with the equation for that, it's basically like taking this line over here, our y, our prediction, minus what our model predicted squared. And this y hat over here is basically this equation over here. This equation over here. So this equation can be written as like y equals y minus mx and plus b over here and squared. So over time, we start out with an assumption like 2.5 and 5. Then once we calculate it over like all these data points over here, so this is going to be like, the summation, going to sum everything all the way from like all the way to n. So from 1 to all the n, which n is like the total number of data points. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's like 10 over there. So once we do the summation of all of this, and let's say we get an error of like 200 at the start, then that is too much. Then we have to update our coefficients m and b. So when we update it, so basically our next line could be something like this over here, and let's say the error could be like 109, 160, let's say for example, and we keep on updating it. We update again. So let's say our next line could be like over here, and which then our mean square error could be like 120. And we update it again, then we could get this line over here. So our best fit line, let's say about 90. And the way that we stop using graded descent is like our stopping factor is like if our coefficients m and b are not changing over time. So then we write some set of rules that, okay, yeah, this is the time we're going to stop. And the way that we update it, of course, is taking like the second derivative of this equation over here. So that's like a really small idea behind linear regression. So the next algorithm that we're also going to talk about, before then, any questions?